Hi, and welcome to another online lecture for General Physics 2. This one deals with the broad topic of the interference of light waves with one another. There's three specific phenomena related to that we're going to talk about, and that is Young's double-slit experiment, which you've seen in the lab, the phenomena of thin film interference, which we will not look at directly in the lab, but you may have seen in your life if you've ever played with bubbles, and finally the phenomena of diffraction. So first we're going to start out with the concept of interference. We've said this before, but just a reminder that we say when two waves of any kind arrive at some point in phase with each other, and that means a peak arrives there from one wave while the peak of another wave arrives, that we get something called constructive interference. When the peak of one wave arrives at the same time that I call it the trough, or I guess the negative peak of the other wave arrives, they cancel out and we get something called destructive interference. We've seen this before in thinking about what happens with standing waves and pulses on springs, etc. One thing that we might note from these two pictures, because that's going to foreshadow where we're going with this conversation, is that the distance that each wave travels from its own source need not be the same. They can be different from one another, but we do need to look for patterns in how those two distances relate to each other in terms of the number of wavelengths. So for example, in this picture, light from source 1 has traveled 2 1/4 wavelengths, light from source 2 has traveled 3 1/4 wavelengths. Whereas in my other picture, light from source 1 has traveled 2 3/4 wavelengths, and light from source 2 has again traveled 3 1/4 wavelengths. And that difference in path length actually determines whether there will be constructive or destructive interference at a given point. One of the challenges of studying wave phenomena and light is, like everywhere, how do you draw a diagram of what you're seeing and how do you make sense of that diagram? So here is a diagram that I've drawn, which is an attempt to picture what you would see if you had two sources of waves, say two fingers tapping on the surface of a container of water or something like that. So here's one source that would be in the center here, and it's moving radially outward in all directions from that source. So the dashed lines can be thought of as a trough, and the bold lines could be a peak. And then here's the next trough, and the next peak, and the next trough, and the next peak, etc. Well, the second source is a close distance away, and it's doing the same thing. So if those are both simultaneously sources of waves, there's going to be many, many regions where some aspect of a wave from one source overlaps a wave from another source. Here in the middle, for example, I have a place where a crest is overlapping a crest. Here's a place where a trough is overlapping a trough. Here's another crest overlapping a crest. Here's another trough overlapping a trough, etc. And if I connect all of those points together, they actually form lines, and these are called lines of constructive interference because they're where the maximum wave action is taking place. It's going to larger amplitude oscillation than it would with either wave individually. So there's one right in the middle, but there's another off to the side as well, where I have, again, trough, trough, crest, crest, trough, trough, crest, crest, etc. In between those, notice here I have a place where a crest meets a trough, and then a trough meets a crest, and a crest meets a trough, and a trough meets a crest, etc. Those are going to be places where the waves are canceling one another out, and we can call those lines of maximum destructive interference. Very often they're called nodal lines. Well, again, I mentioned we're going to be looking at the path length differences in these patterns. The path length difference of a two-source interference here, when I have constructive interference, comes in whole integer number of wavelengths. So any point that I would pick on this red center line would be the same number of wavelengths away from the source on the right as it would be from the source on the left. So the path length difference at every point along this line is 0 wavelengths. If I pick the blue line where I get nodal lines or destructive interference, every point on that line is 1/2 wavelength further from the source on the left than it is from the source on the right. Then I find a another maximum constructive interference line, and everywhere along this line, those points are one whole wavelength further from the source on the left than they are from the source on the right, and that produces constructive interference again. Over here, I get a place where I am 1.5 wavelengths further from one than the other, and that's it for this particular pattern. But if these two sources were a little bit further apart, there would be additional lines of maximum constructive interference and additional nodal lines. Thinking about these overlapping waves can help us understand what's happening in Young's experiment. So Young is the first person credited with doing this particular experiment. He shone light actually first through a single slit to get a nice narrow beam of light that actually subsequently spread out a little bit after that slit, just like we saw light from a single slit spreading out. It became wide enough to illuminate 2 slits, and then the light that traveled through those 2 slits formed a pattern on the screen much like you saw in lab today. Now, this was somewhat of an experimental tour de force, because what becomes important in this experiment is that if you want to see a clean interference pattern, bright, dark, bright, dark, bright, dark, you need monochromatic light. That is, light that is emitted at a single wavelength or a single frequency. And lasers do that well, but it's not so easy to get single frequency light from a non-laser source. A standard light bulb, for example, emits a whole range of frequencies of light. So again, in this particular experiment, the 2 narrow slits act like new sources of light, and each of them are producing light, but they're producing light that is said to be coherent, and that simply means that when they leave these 2 slits, the 2 light waves are in phase with one another. They're emitting, if you will, crests crests from both slits at the same time, troughs from both slits at the same time. The single slit is here simply to limit the direction of the approaching light and to spread out the beam so that it hits both of these slits. The laser limits its own direction by being a fairly one-directional beam of light. And where we get the light piling on top of light constructively, we get a bright spot on the screen. Where we get light and light interfering destructively, we get a dark spot on the screen. So we want to work a little bit on the geometry of what's going on in Young's experiment. So here is the same apparatus, but now we're looking down from above. So here is the opening slit 1, here's the opening slit 2, and here's the screen over here. And the distances are not at all drawn to scale in this picture, because the slits would need to be typically much closer together relative to the distance between the slide and the screen. But bear with us, this is just for labeling and working out the geometry. So if I have light that travels from both slits to the same point on the screen, I get constructive interference, and that results in a bright spot on the screen, and this is where those 2 path lengths are the same. If I move slightly up on the screen, there will be a spot where there is a dark spot where destructive interference is taking place. What does that mean? Well, it means light traveled further from source 2 than it did from source 1, or slit 2 and slit 1. How much further? Has to be half of a wavelength, because half of a wavelength will mean that when the crest of a wave from source 1 arrives at this spot, the trough of a wave from source 2 is arriving at the same time. Then later, when a trough of a wave from source 1 arrives, a crest of a wave from source 2 arrives, and they are always canceling one another out. So the length is greater than the length from source 1 by a half amount of wavelengths. Go out here a little bit higher still, you'll get a spot where you see a bright spot, and this is a spot that must correspond to light traveling from slit 2 a whole wavelength further, so that once again the 2 waves are in phase when they arrive at this location. And you could keep repeating this thinking across the width of the slit. And if you look at the screen, you observed in the lab a pattern that looks something like this. So we get bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, bright spot for at least several fringes on either side of that central fringe. That's often called the 0th order fringe, and then if you're counting fringe numbers, you count 1, 2, 3 in either direction as you move away from the central fringe. If you were to plot the intensity of the wave at any of those points, it would be the most intense at the center, and then the intensity drops off with distance, which is one of the reasons you saw sort of those dark spots off to the side of the central bright area where you had bright, dark, bright, dark, bright, dark. So let's again try to quantify what's happening in Young's experiment. Well, if I arrive here at a point on the screen, light traveled along two different paths to get there. It traveled slightly different angles to get there, but we're talking slight, because if you are thinking about a distance on the screen that is a couple of millimeters away from the center bright spot, and your screen is a meter away from your slide, the difference in these two angles is tiny, tiny, tiny. So we're going to treat them as being about the same, even though the angle from S2 would be slightly larger than the angle from S1. The two slits are separated by some distance d, and so if we look, the difference in the path, so light from source S2 has to travel further distance to get to that spot on the screen. We're going to call that path length difference delta L. That would be the difference between L2 and L1. And turns out, because that line that forms this right triangle would be essentially perpendicular to both of the lines that the light is traveling along here, we form a nice little right triangle in this location. The angle here is the same as the angle theta on the original diagram. In other words, when I angle this up by some theta to travel along this path and get to the screen, that's the same theta that is in the shaded triangle on the diagram. The way you can see that is the dashed line is perpendicular to the screen, or the slide rather, and now this line that I'm drawing to mark off the path length difference is perpendicular to one of these rays of light or light paths. So that's a 90-degree angle, this is a 90-degree angle, and from that you can deduce that if this has to be theta, so does the angle between these two lines. Okay, so I have a right triangle where I know theta, I know the opposite side of the triangle, and I know the hypotenuse of the triangle, and that's going to come into play in just a second. At different angles theta, you get the first, second, third, fourth, etc. bright spot on the pattern on the wall. Well, sine of theta relates the opposite side, the path length difference, and the hypotenuse, which is the distance between slits, and we can write that sine theta equals that path length difference over d. If we're talking bright fringes of a double slit, we want that path length difference to be whole numbers of wavelengths. So 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, etc. And in fact, for completeness, we include 0 because we get a bright spot in the center of this pattern. If the path length difference is 0, we should also get a bright spot. So we can write that we can predict the angle where we'll get bright fringes by this relationship relating the sine of the angle to the whole integer number of wavelengths over the distance between the slits. You can also predict the positions of dark fringes, because those dark fringes should happen when you have a path length difference of half a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, etc. So you can rewrite the expression to be m plus a half lambda over d, where m is 0, 1, 2, 3, etc. Or you can in fact use the same expression that we used for bright fringes and just change the indices to half, 1.5, 2.5, 3.5, etc. Your preference. It's also, however, convenient to predict where those fringes will be spatially rather than just predict the angle theta. And so we typically call the distance from the middle of the center bright fringe, or the 0th fringe, out to whatever point we're studying, we call that distance y. If we call the distance from the slits to the screen L, notice that we've formed another right triangle in here, also involving the angle theta. And from this, we can write the tangent function, which relates the opposite and the adjacent sides, to say that the tangent of that theta is equal to the fringe spacing distance y over L, which is the distance from the slits to the screen. Or we can write y equals L tan theta if we're solving for y. Well, if the angle theta is small, and this is an if that is not always true, it is very true in the data you collected in lab dealing with the double slit, which is why we got the final model that we did. But if theta is small, the sine of theta is approximately equal to the tangent of theta. So here's the tangent of theta, but we had a result on the previous slide relating the sine of theta to other pieces of the system, and sine of theta we showed was m lambda over d. So if sine theta is approximately equal to tan theta, we can write y over L from above equals m lambda over d from the previous slide, and move the L over to the other side to predict the fringe distance to whatever fringe it is you're counting is equal to that fringe number times the wavelength times the length between the two divided by the distance between the slits. A few conceptual questions that you can use that relationship for to practice. Suppose we viewed this screen in a two-slit experiment, and the viewing screen were moved closer to the double slit apparatus. What should happen to the interference fringes? Would they move closer together, move further apart, or the spacing does not change? Here, like always, I would encourage you to pause the presentation and come up with an answer on your own before listening to my response. My response would be that the fringes move closer together. If I keep everything else the same, moving the slit closer to the screen would reduce L, the distance between those two things. And if L is smaller, Y is smaller, and Y is the distance between the center bright fringe and whichever number of fringe I'm counting, and that number would get smaller. That would mean these bright fringes would get closer together on the screen. What would happen to the brightness of the interference fringes if the viewing screen in a two-slit experiment is moved closer to the double slit apparatus? Is this question even different than the previous one? Sorry, I didn't catch the difference here. What happens to the brightness of the interference fringes if they're moved closer? Do they get brighter? Do they get dimmer? Or does the brightness not change? The answer turns out that they get brighter, but this is not something that can be predicted from the equation here. Notice this has nothing to do with intensity. This only predicts the location of those fringes. And the argument that they will get brighter comes from the fact that this happens to all light. As light travels, it spreads out. The more it spreads out, the more diffuse it is, the less bright or intense it is at any given point. So if I move the screen back toward the double slit apparatus, I'll be closer to the source of those waves. They will be less spread out than they were before, but they will be more intense and therefore brighter. If I have light that has a certain wavelength, lambda 1, and it illuminates a double slit apparatus and produces the interference pattern that we see here. If light of wavelength lambda 2 is used instead, and we see those fringes get closer together, how do the two wavelengths compare to each other? Well, here, the distance from the center bright fringe to any fringe number has gotten smaller, so y for any value of m is gotten smaller. If that's the case, since it's directly proportional to the wavelength lambda, lambda must have also decreased as well. Hence, lambda 2 is less than lambda 1, which is option 1. So here's a quantitative practice problem. Two very narrow slits are spaced 1.85 micrometers apart and are placed 36 centimeters from a screen. What's the distance between the first and second dark lines of the interference pattern when the slits are illuminated with coherent light with a wavelength of 552 nanometers? In this situation, because the narrow slits are so close to one another, the angle theta is actually not small, and the only thing that's going to change about our approach is we cannot use the equation that was pieced together a few slides ago. We'll have to use the equations that actually have the angle theta in them. So how do we approach this? Well, I draw a sketch of all these things first. So here is the distance to some spot on my screen, and that distance from the center bright spot is called y. we're looking for the distance between the first and second dark lines of the interference pattern. So we're actually looking for a distance between dark here and dark here. Turns out it's going to be the same distance as it would be between bright and bright, but we'll go with the problem as written and solve dark and dark. There's a path length difference, and that path length difference, delta L, is d times the sine of whatever the angle is. So the path length difference between these two rays is d sine theta. They're going to destructively interfere, so the path length difference should be half integer values. In other words, we're looking for the difference between where the path length difference is a half a wavelength and the path length difference is 1.5 wavelengths. So the first dark fringe is going to occur when m equals 0, and that's going to mean the path length difference is 1/2 a wavelength. And the second dark fringe, m equals 1, so d sine theta there is 1.5 wavelengths, or 3/2 of a wavelength. And the fringe distance y is related to the distance L between the slit to screen distance by this expression. This should be an L. I guess it's not a typo. What is that, a right-o? Anyway, tangent of theta equals y over L is written correctly on here. So here is an expression that relates theta to the number of wavelengths. Here's an expression that relates theta to the relevant distance y. We have to combine those two. So the difference in y positions would be y2 minus y1. That would be L times the tangent of theta 2 minus L times the tangent of theta 1, which we got from rearranging this expression right here. Well, theta 2 and theta 1 can be gleaned from these 2 points that we've identified as the locations of the first and second dark fringes. So you solve each of those expressions for theta, and you get theta is the inverse sine of lambda over 2d, or 3 lambda over 2d if you do the algebra on these expressions. So a final expression is I get L times the tangent of the inverse sine of 3/2 lambda over d minus tangent of the inverse sine of 1/2 lambda over d. And if I plug in all of my numbers, it looks something like that. The wavelength in this case is 552 nanometers, so that's 5.52 times 10 to the minus 9 meters. And the slit spacing is 1.85 micrometers. That's 1.85 times 10 to the minus 6. And the 36 centimeters is the distance from the slits to the screen. That's out here. Crunch all those numbers and you get about 12.6 centimeters, or 0.126 meters. So that is a much larger distance than you were measuring in your patterns in the lab. However, if you think about the widest spacing you observed with two-slit interference, it happened when the two slits were closest together, and that was at 0.125 millimeters. So if you keep making the slits closer together, as they are in this problem, the spacing of the pattern should get further and further apart. We're going to go on and talk about the second of the three main topics for this, and that is the phenomena of thin film interference. If you've ever played with bubbles, you may have observed that the bubbles contain a multitude of colors, and there are blue, red, green, yellow, whatever color bands within those bubbles. How do they get there? Maybe you've never concerned yourself with that question, but that's something we're going to do here. The same phenomena, by the way, happens if you see like oil on top of a puddle. You see all sorts of different shimmery colors in there. Well, this is another demonstration of the interference of light waves, and it occurs in more common places than Young's double slit experiment. We don't always have two narrow slits and a laser light in order to see that, but bubbles and other thin films are something we have more, at least, observational experience with. Well, it comes from the idea that when light passes through a boundary between two materials, part of that light is reflected and part of it is refracted. And I guess I should just say transmitted at this point, because we don't care about what the refraction means quite yet. So part of the light is reflected and part of it is transmitted into the new material, and we've worked in tutorial on building a model for what happens with light in that case. So it turns out light can end up interfering with itself because some of the light that gets transmitted into a new material will reflect back at the next boundary and then run into the light that was reflected at the first boundary. And we'll see that diagrammatically here in a minute. In fact, there is a picture where light strikes a boundary between air and gasoline, and part of that light gets bounced back to the eye. That's path 1 on the diagram. Part of that light continues into the gasoline and then is bounced off of the boundary between the gasoline and the water, comes back through the gasoline, and then is transmitted back out into the air and through the air into the eye. There's a couple of parts of this that weren't diagrammed. Part of the wave would actually continue into the water, and part of the wave here would actually reflect back into the gasoline, and then it would again interact with this boundary. Part would be reflected, part would be transmitted, etc. But we're just focusing on the basic path you need in order to observe thin film interference. So the transmitted portion at the first boundary. Part of that is reflected at the next boundary, and if these two waves that are now coming into the observer's eye constructively interfere, the observer is going to see a bright spot right there. If they destructively interfere, you're going to see a dark spot. Now, if you look at a bubble, you don't generally see bright spots and dark spots. You just see different colored spots. And this is because different colors of light have different wavelengths. So while the thickness of a thin film may be appropriate for, say, blue light to be constructively interfering, it might also make red light destructively interfere. So I will see that portion of the bubble as a bright blue color. Another portion of the bubble might exhibit constructive interference for yellow light and destructive interference for another color of light. And so you end up seeing these colored bands where the color that you see most strongly is the color that is being most strongly constructively interfered with. And if you don't see a particular color, that's because that color is at that angle and that position undergoing destructive interference. So another note about solving these thin film problems is that the wavelength that's important to our considerations here is the wavelength of the light within the film, not the wavelength in the vacuum or air. So recall from tutorial, we talked about two pulses moving from a fast-moving medium to a slow-moving medium, or vice versa. Well, when it goes from a fast-moving medium to a slow-moving medium, recall that the pulses get closer together, or a single pulse gets narrower, and that is consistent with a change in the wavelength of that pulse. And that's in fact what we see when light travels through materials as well. Light actually slows down when it goes from air into gasoline, and when it slows down, the wavelength of the light changes as well. The one piece that does not change is the frequency or the period of that, and that's related to the questions about the time between pulses that we explored in the tutorial. So we define something, and we'll see this again in a couple of subsequent discussions, called the index of refraction, which is the ratio of the speed of the light in a vacuum to the speed of light in a given material. And we just call that a number. Of course, speed over speed is not going to have any units, so indices of refraction get units of nothing. There's a number. So the speed of light in a vacuum is typically abbreviated c in most physics textbooks. The speed of light in a material is abbreviated with a v, and both terms can be divided by frequency. Why not? That's like dividing by 1. So c over f equals v over f. Well, speed divided by frequency is wavelength. And so the index of refraction can also be written as the ratio of the wavelength of the light in the vacuum to the wavelength of the light within whatever material is forming the film. In this particular picture, that would be gasoline. That means that the wavelength of the light in the film is equal to the wavelength of light in a vacuum divided by n, which is the index of refraction. So for example, of gasoline, that is 1.4. So if the speed of light is 3 times 10 to the 8th meters per second in a vacuum, then it would be moving at 2.1 times 10 to the 8th meters per second in gasoline. Recall as well this from tutorial, that when we had a wave moving from a less dense medium into a more dense medium, that the transmitted pulse was narrower, and we just talked about that with regards to the wavelength. But the reflected pulse was the same width as the incident pulse, however it was flipped, so it went from being above equilibrium to being below equilibrium. Where we're going to go with this is to say that the reflection here going from a less dense medium to a more dense medium is consistent with a phase shift of 1/2 a wavelength. So where there used to be a crest, there's now a trough. Where there used to be a trough, there's now a crest. That's a 1/2 a wavelength of shift ahead or behind in the wave's travel pattern. When we had the reverse, when we had the pulse coming in from the more dense medium into the less dense medium, the reflected pulse stayed on the same side of equilibrium as it did. So we're going to use that model here as well. When you go from more dense to less dense, the reflected pulse stays on the same side of equilibrium, and that is analogous to no phase shift happening. We're going to need that result for predicting the thin film behavior here. Okay, so here's another picture showing a phase change. If my incident wave comes in like this, and my reflected wave is flipped around, that reflection at the boundary is equivalent to a phase change of 1/2 of a wavelength. When light travels, however, from a larger refractive index toward a smaller refractive index, we get no phase change upon the reflection of the boundary. So we defined the refractive indices in terms of the speed of light, or the speed of a wave in that particular medium relative to that speed of that wave in a vacuum. However, you can also think of refractive index as a measure of, say, optical density, which is going to be analogous to the mass density for the waves on the springs that we've previously looked at. All right, so a couple of more questions to practice to help us get to what we want to be at to understand this thin film. This is something we've seen before. If I have these two individual wave patterns and I add them together, will I get A, B, C, or D? Correct answer is that I get A. They are constructively interfering, so here both amplitudes will add together to give me an overall higher amplitude. And also here where the amplitude is below equilibrium, these two will add up and stretch the wave down further. The problem with B is that the wavelength has changed, which is not consistent with what we observed. C would show what would happen if these two waves were canceling each other out, and D would be the extreme, but impossible in this situation where the waves don't have the same amplitudes. What if you had these two waves? So now I get the same first wave, but now I've taken my second wave and I've flipped it around. Well, it's going to produce less amplitude, so that's either going to be B or C. Let's see which one it would be. Just to the right of the origin, the wave has more. The one wave has more amplitude below equilibrium than the one does above equilibrium. So the net result of adding those two things is going to be a wave that goes below the equilibrium position, and that is consistent with pattern B here. Relative to the higher amplitude wave, the lower amplitude wave is shifted by how much? Here's where this concept of phase shift comes in. If I have a peak for the higher amplitude wave at about 2.4 on this, a little bit less, maybe 2.35 or something like that, then where's the lower amplitude wave? Well, the lower amplitude wave peak is back here at 0.8, or it's ahead here at nearly 4. But what's important is the number of wavelengths that would be, and I would have to shift this lower amplitude wave forward by 1/2 of a wave cycle, or 1/2 of a wavelength, in order for the amplitudes to line up. Hence, the lower amplitude wave is shifted by 1/2 a wavelength relative to the higher amplitude wave on this particular picture. So back to a problem with thin films and gasoline. If we assume the thin film of gasoline floats on a puddle of water and sunlight falls almost perpendicularly on the film and reflects into your eyes, sunlight is white, but since it contains all colors, this film of gasoline that we look at has a yellow hue in the specific place that we're looking because destructive interference eliminates the blue light from the mix of sunlight there. The refractive indices of the blue light in gasoline and water are 1.4 and 1.33 respectively, so determine the minimum non-zero thickness of the film. So there's a lot of special notes in here. Sunlight falls almost perpendicularly on the film. The reason that we're saying almost perpendicularly is we're going to assume the path that the light travels through the gasoline is equal to twice the thickness of the gasoline. If light came in nearly parallel to the boundary, it might travel a much greater distance than the thickness of the gasoline, both down through the film and then back up through the film, and that would change the assumptions that we're making in this particular problem. So almost perpendicular is cueing us in to think exactly perpendicular. However, you need it to be at a slight angle to get the interference effect that you're observing. I think maybe that's the only assumption that we have to worry about at this stage. So let's put it in this form and commence with solving this thing. There's already a diagram right there, and I perhaps should have scribbled on the diagram, but I drew my own. When light travels in air and bounces off gasoline, that's a reflection event. And that reflection event is consistent with a phase change of 1/2 of a wavelength, just like a wave on a spring going from a less dense to a more dense medium. The reflected portion of that pulse was flipped around and it was on the other side of equilibrium. The wave that continued into the gasoline bounced off of the boundary between gasoline and water, and there the refractive index of water is smaller than the refractive index of gasoline, so the model predicts that there is no phase change at that particular reflection event because it's like bouncing off of a free end reflection. This is less optically dense than the gasoline is. That's going to become important in our solution. Ray 1 in going here and then coming up to the eye, or light path 1, has a phase change of 1/2 of a wavelength right here. Ray 2 has no phase change, but Ray 2 travels a greater distance because it goes through the thickness of the gasoline film twice, whereas Ray 1 does not do that. So the path length difference between the two paths that light takes to reach your eye is whatever distance Ray 2 traveled minus whatever distance Ray 1 traveled. Well, Ray 2 traveled an extra distance of 2 times the thickness of the light in that film of gasoline. Ray 1 didn't travel any extra distance, but it essentially did because it underwent a half wavelength phase shift by bouncing off the air-gasoline surface. So what is the condition for destructive interference? Well, destructive interference happens when the path length difference is half a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, etc. We want this to be the thinnest possible film based on the problem statement, the minimum non-zero thickness. So we're looking for an interference that is 1/2 of a wavelength of path length difference. So if I plug that in for delta D, I get that delta D equals 2 times the thickness of the film minus 1/2 a wavelength. And I want the path length difference to itself be 1/2 a wavelength. That means if we solve for the thickness, we can write 2t equals 1 wavelength, or t equals 1/2 of a wavelength. The only catch here is that thickness equals 1/2 of the wavelength of the light in the gasoline itself. And the wavelength of the light in the gasoline itself is the wavelength of the light in a vacuum divided by the index of refraction of that particular material. I'm using a generic film, but that's gasoline in this particular problem. So we plug in numbers. The light in a vacuum is 469 nanometers. The index of refraction is gasoline is 1.4. And so if you crunch that out, you get 168 nanometers, which means if you have gasoline that is 168 nanometers thick, you would see it as yellow because the blue light would be destructively interfered with. Of Of course, it could be thicker, and the path length difference could correspond to 3/2 wavelengths, 5/2 wavelengths, etc. But it couldn't be any smaller than this, or you wouldn't get the blue light to be canceled out and the yellow light to be reinforced. So back to bubbles. Different colors in this thin film arise because the thickness is different in different places in this bubble. Hence, the different thicknesses will correspond to constructively interfering certain colors while destructively interfering other colors, and then you move to a slightly different thickness and a different pattern emerges. And the color you see also actually depends on the viewing angle. So in the previous problem we assumed the light came in from the sun perpendicular to the boundary, but if we hadn't made that assumption, the path that the light traveled through the film would be greater than the thickness of the film, and that can correspond to seeing different colors. There's another way you can use this phenomena. You can actually measure the thickness of a very thin object optically. And the way you do it is you take a couple of pieces of glass and you put some thin object in between one end of those two sheets of glass. In this particular picture, it's a sheet of paper. If we illuminate this whole thing with monochromatic light, meaning light of one color or one wavelength or one frequency, we end up seeing a whole region of bright and dark fringes on the glass plates. And counting those fringes will actually tell you something about how thick the object is that you've placed in there. So this is a sheet of paper, but you could use this technique for measuring the diameter of a human hair, for example. Well, what's happening? The monochromatic light is coming through, and there's air, and so some of it bounces off here before it transmits into the glass. But the glass mostly allows the light through. After all, this is why we use glass. It's mostly transparent. Some of it reflects at the boundary between glass and air, here in the gap in between. A portion of it continues to travel into the gap that contains the air and then bounce back out go in the other direction. And then continue back up through the glass and be observed by a viewer up above. Again, there's many more reflection events that are happening everywhere here, but we're just focusing on comparing the light that traveled along these two paths. So, if we have this situation and we have green light with a wavelength of 552 nanometers, how many bright fringes would occur between the place where the plates touch over here and the edge of the sheet of paper, which we're given the thickness of, which is 4.1 times 10 to the minus fifth meters. Well, let's go ahead and diagram that again. You don't have to, but we want to point out that here, when light is going through glass and bouncing off back into the glass, it's bouncing off of air. Air has a lower index of refraction than glass does, so this event right here mimics a free end reflection, and there's no phase change associated with the light that bounces off at this boundary. But the light that was traveling in the air in the middle of that wedge will bounce off of glass. That's like fixed end reflection, and so this reflected light will undergo a half wavelength phase change. It'll be transmitted back through the glass, and then we're looking at how 1 and 2 interfere with each other in terms of determining the number of fringes. So ray 1 has no phase change, ray 2 has a phase change of a half a wavelength, and we can find the path length difference between those. Ray 2 travels an extra 2 thicknesses of whatever the gap is in between the sheets here, and ray 2 also undergoes a half wavelength phase change. Ray 1 doesn't travel any extra distance, so we just plug in a 0 for that. Therefore, the path length difference is going to be 2t plus half a wavelength. Well, constructive interference, and we're told information about bright fringes, or we're queued for information about bright fringes, so we're thinking constructive interference. We're looking for constructive interference, and that happens when the path length difference is some whole number of wavelengths, m times lambda. So the path length difference we deduced from the bottom part of the screen, 2 times the thickness of the air gap, plus the 1/2 wavelength for the phase shift of one of those waves of light, has to equal a whole number of wavelengths of light. Therefore, m, which is the number of fringes, has to equal 2 times the thickness plus half a wavelength divided by the wavelength, or 2 times the thickness divided by wavelength plus 1/2. If you plug in the thickness of paper for the thickness of the air gap, essentially we're thinking about the last place where we get constructive interference before we run into paper. And you divide by the light. Here we don't have to do any conversion because the difference happens within the air, and the index of refraction of air is 1, so the wavelength of the light in the air is going to be nearly equal to that in a vacuum. I find that M calculates out to be 149. Hence there would be 149 of these bright spots all along this sheet of glass, which would be illuminated in this particular situation. Where you would more commonly use this for a lab reading is you would not know the thickness of the sheet of paper. You would put it in this system. You would count your 149 fringes, and then you would work backwards through this calculation to work out what T, the thickness, must be of the object that you're putting in between the sheets of glass. There's other places where you see this phenomena. In fact, when you see it in ring patterns, it's often happening when something doesn't have uniform thickness. You'll get these things called Newton's rings, and they happen over and over and over again because each time you jump out to the next ring, you have one more wavelength of path length difference or one less wavelength of path length difference. And so you can form these actually somewhat beautiful patterns on puddles or what have you, or with lenses that form these regular patterns. And again, counting the fringes can tell you something about the thickness, or knowing something about the thickness of the material can tell you something about the number of fringes. Interference is also important in the operation of compact discs and things of that nature. Of course, these are rapidly fading from our lives, but basically with a compact disc, you can shine light down on to the compact disc. That light bounces back up off of the compact disc, and depending on whether that light interferes constructively or destructively can tell you how far the surface of the disc is from the source of the light. And that can be used to tell you whether that portion of the disc is coded as a 1 or a 0 and turn that into the digital music that we are all accustomed to listening to. I won't mention all of the physics behind this, but one of the experiments that established that space was indeed empty and not filled with something called luminiferous ether was experiments with the Michelson interferometer. And the Michelson interferometer was an experiment where they were actually looking for this ether in the universe and trying to characterize its properties. Turns out they couldn't find it there. It involved taking a beam of light, splitting it into 2 parts, sending those parts through different parts of the system, and then having those parts come back on each other and looking at the interference pattern. And basically what that ended up showing is that it didn't matter how they turned the interferometer, light traveled at the same speed in all directions, which would not happen if space were in fact filled with some sort of substance that slowed light down slightly in one direction and not in another direction. We're going to wrap this discussion up just by talking about the phenomena of diffraction. Diffraction is the spreading out of any wave. Here we're thinking specifically about the spreading out of light. So diffraction is the bending of waves around obstacles or the edge of an opening. And so when I have a plane wave front running into my opening, what I observe on the other side is that the wave seems to bend on the edges and travel outward in sort of a curved fashion after passing through the opening, whereas before all of the wave fronts were parallel to one another. One way you can think about what's happening here is to think about each point on the wave front acting as its own little wave source, so that each point on the wavefront that runs into the opening becomes essentially its own little point source, making this spherical wave pattern. And if you add all those spherical wave patterns, you can predict the shape of the wavefront that emerges on the other side. And one principle that seems to be true is that you have to have the opening relatively small relative to the size of the wavelength of the wave that you're sending it through in order to observe diffraction. We observed diffraction in the lab when we sent light through single slits that were fractions of millimeters wide. But if you shine light through a doorway, you don't at least noticeably notice the bending of light. However, sound waves that go through a doorway seem to bend and go off in other directions. And the wavelength of sound waves is much closer to the width of a doorway than the wavelength of light waves is. So I guess we just touched on that. The extent to which wave bends around the edges is determined by the ratio of the wavelength to the width of the opening. So here is an opening where I'm sending in parallel water waves, and notice not a whole lot of bending happens with that wave as it passes through the opening. If I make that opening significantly narrower, there is a lot more bending or diffraction of that wave that happens after that wave has passed through the opening. So we saw double slit interference in the lab, but we also saw single slit diffraction. If light didn't bend, it would predict that the light would all show up in one spot on the screen, but instead what we observe is when we shine in the lab the laser light, but in truth any monochromatic light, through a narrow opening, that we get a really broad center spot that is bright, and then dark spots, and then more bright spots and dark spots as that pattern emerges out. Well, the way we make sense of this is to, again, imagine that when the light comes and hits this opening, that instead of that opening acting as a single source of light, it's acting as a multiple source of light for many, many different points of light. And then each of those are sending light out traveling toward the screen, and we can look at how those things interfere with one another. So the key to all of this is to imagine that any opening is filled with multiple sources of whatever kind of wave you're thinking about. In this particular situation, that would be light waves. So it turns out it's easiest when you're doing diffraction to figure out where the dark fringes are located. So here's the midpoint, which we know is bright in the middle of single slit diffraction. Out here is the first dark fringe. And that dark fringe would occur when light, for example, from source 3 was 1/2 wavelength of travel distance greater than light from source 1. Because if that were true, then light from source 2 would be 1/2 wavelength difference from light from source 4, and they would destructively interfere. And you can imagine there's a point right below 1 that would destructively interfere with a point right below 3, and a point right below that would destructively interfere with a point right below that. And so there would be these pairs of points that would send light off to some distant location over here, all of them destructively interfering with each other. And the second one would happen when, say, light from point 2 was 1/2 a wavelength further than that from 1, which means light from 3 is a wavelength further, light from 4 is 3/2 a wavelength, light from 5 is 2 whole wavelengths, and etc. So the sign of the angle out to those dark spots, is again given by the whole number of wavelengths, m lambda, divided by W, and W is the width of the slit opening. When you look at a diffraction pattern on the graph, you see a wide center bright spot where most of the intensity of the light is occurring, those dark spots on either side, and then smaller bright spots off to the side alternating with dark spots as well. Typically, we use the same symbols for everything. Y is the distance from the bright fringe out to either the dark or the bright fringe on the pattern. L is the distance from the opening over to the screen. Diffraction, however, so the key difference is it produces a central maximum that's wider than the other maximum. What you may have noticed in the lab is that when you were looking at the 2-slit interference pattern, which had small little light and dark and light and dark and light and dark in the center, if you step back and look at it, it looked exactly like the single slit pattern, because that bright dark, bright dark, bright dark, bright dark in the double slit pattern actually fills the space that is consistent with single slit diffraction. So naturally, when you're looking at a double slit pattern, you're looking at a double slit overlaid on top of a single slit pattern. You can also have something called a diffraction grating, and a diffraction grating is more than a single slit or a double slit. It's something that has multiple, usually hundreds or thousands of slits, and it closely mirrors what's happening with a double slit interference. So if you have multiple places where you let light through, there will be, again, lots of spots on the screen where you get constructive or destructive interference. The key difference when you use a diffraction grating with, say, 100 openings rather than 2 is that you get narrower bright spots on the screen. They're not as spread out and oscillating sinusoidally in terms of intensity. So you may have noticed that when you're playing around with the multiple slit slide in the lab. If you crank it over to where it has multiple slits, these bright spots get more defined relative to each other, and it's easier to actually take measurements with that. The diffraction grating has the same principal geometry to predict where those bright spots are as a double slit pattern does. Again, we're looking at places where we're a whole number of wavelengths, path length difference, or 2 wavelengths, or 3 wavelengths, what have you. And again, as I mentioned, we get this kind of funny interference pattern where we get a really bright center spot, another bright spot out here, and in between, almost imperceptible. It's really dark, but you get these smaller maxima in between there. But the bright spots themselves are much narrower than they are when you use just the double slit alone. So one thing to briefly mention here at the end, because some of you work in fields where this is important, this is the basic physical principle behind what happens with X-ray diffraction as well. And X-ray diffraction was used to figure out how atoms within a crystal must be spaced relative to one another, because in diffraction through a grating, you send in light and it interferes with each other. Well, if you hit a crystal with some sort of light, and it's actually typically not visible light that's used, the light that bounces off each of those atoms can interfere with light bouncing off of other atoms and give you a diffraction pattern that will provide you with information about the structure of that particular crystal. The challenge is we can't use visible light because we need light that is shorter wavelength in order to actually see a pattern. And so typically X-rays get used for these kinds of studies, and so you may have heard the term X-ray diffraction talked about. That's literally what they're doing, bombarding something with a bunch of X-rays and then looking at the X-rays that have bounced off that structure and see how they're interfering with one another. Watson and Crick, in fact, used X-ray diffraction as one of the tools they used to figure out what the structure of DNA is. And when you do X-ray diffraction on materials, these are just a couple of images grabbed from a textbook, you get patterns like this. But these, of course, would be the bright spots where you're getting maximum constructive interference, and measuring the spacing between those bright spots and knowing how far things are apart from each other will allow you to calculate how far the atoms within a crystal structure must be relative to one another. So this concludes the online lecture for General Physics 2 dealing with the concept of the interference of light. Hopefully this was a useful resource for you, somewhat lengthy in this particular case. As always, if you've noticed any errors in the presentation, I would appreciate you letting me know about that. Thanks.